Hello, students. Welcome to Mech-3, Simple Machines. Uh, this lab is part of a Department of Physics and Material Science at Chiang Mai University lab module. So first of all, when you talk about machine, you would think of things that were designed to produce a work of humankind, and one of the popular sources from the movie Terminator. So machines are made to do works that human don't want to do. So, in this lab, we're going to be talking mostly about simple machines and machines throughout the history. Humankind have developed and designed many different machines in order to help us achieve what we want to do with minimal work. And by minimal work, I mean minimal force. When we talk about force, then again, let's say we want to lift an object through the y-axis, right? So in this case, there would be two concepts that we want to talk about: is the velocity ratio and the mechanical advantage. Okay, and the main concept is that you cannot just create energy out of nowhere. So in order to make this happen, we should consider these two cases. So if I were to move this object, this little blue box here, from the bottom all the way to the top, uh, one thing that I could do is basically just lift it all the way up, or I could just put it on an inclined plane and then put it through. So the object would gradually move all the way through. And then from the conservation of energy, that you would know that the work that is done in order to lift this weight all the way up to the top is calculated through y multiplied by w multiplied by y. Or alternatively, you could also say I'm using this force F, which is smaller than the weight W, but I push it for a longer distance S. So by doing this, I would achieve the same amount of work by pushing it through the gravitational potential energy. So you could say that the work done in this path and in this path should be the same. So you cannot create energy out of nowhere again. So W times Y must be the same as F times S. This is from conservation of energy. So if I were to move things around, I could also potentially say if I push F on the other side, Y has to be divided here. So what does this mean? So S is a longer distance here, right? So S divided by Y is going to be bigger than 1 because S is a longer path and Y is a shorter path. So by the merit of having S longer than Y, you would have weight that is like much heavier can be lifted with the force that is way smaller. So imagine lifting something extremely heavy. What would be easier if you were to push it along the inclined plane or lift it all the way up? So this is the same thing as like when you go to when you go to the isotape, like you can say that if you take the route that's really steep, then you would end up being really exhausted. But instead, if you walk the road, which is slightly inclined, then you end up taking a longer path. But then again, you would use a lot less force. Okay, so the ratio between the force that you can get is called the mechanical advantage, or MA, in this lab. So the mechanical advantage would gives you the ratio between the weight that you want to lift versus the force that you're actually using to apply it by using the machine. So mechanical advantage should be bigger than 1 to give you any advantage. Okay, and then again, this is the same as the ratio between the two distance. So if you were to divide the distance s distance y, you would have velocity ratio, which is calculated as v dot r dot. Okay, so ma and br has to be the same theoretically, right? So in a sense, we're using conservation of energy to reserve the amount of force that we have to apply onto the system by increasing the length at which we're doing the work, and then again, by doing so, you you produce the same amount of work with the minimal amount of force. And this is how the machine, the simple machine in this case, help us, not the Terminator kind of machine. Okay? All right. So on the first part, however, there's always friction, right? So friction is when you push this guy all the way up the slope. The friction is always there, right? So friction would come into play. And then again, just for the force, to be able to push this object all the way up to the top, you want to consider the effect of the friction that would actually slow this thing down. So again, this lowers the mechanical advantage in comparison to VR. So you could actually say that by the virtue that the mechanical advantage being lower than the velocity ratio, you could calculate the efficiency of the machine. So if theoretically it should be the same number and calculated and multiplied by 100%, would actually get the efficiency of the machine. And to reverse this logic, since mechanical advantage is the ratio between the force, you can use this relation to estimate the amount of friction that's being applied to the system, which would be doing it over and over. So from here, you would know the weight of the object that you'll be pushing and the amount of force, which is represented by the mass that's you're going to be hanging. And then from there, you could you could actually calculate the efficiency of the machine and then work on the friction and calculate it and put it on the table in this lab. Okay. All right. First part is the inclined plane. So in the case of the inclined plane, you would actually have like the plane that is inclined, and the force is the weight that is being hung on the right side, and on the left hand side, you would actually have the weight that is being hung on this slanted slope. And uh, you have to make the object move by the distance s, and in order to get it move up by the distance y. Okay, so from here you can use the ratio between s and y to first calculate the velocity ratio, and the velocity ratio is going to be 1 over sine theta theoretically. So if the theta is inclination angle, and then again, once you have calculated VR based on what is the s, what is the y, you can put the VR into this equation and calculate the friction in the system. And from there, you could also estimate the efficiency of the machine. From here, this is the actual setup of your part 1 of the experiment, the inclined plane. Given here in this video is a set of plank wood that is set up. So first of all, you want to make sure that the plank is aligned to be 30 degree. So the angle is actually set up properly. So be sure to readjust it and then make sure that the alignment is correct. And that little knob right there can be used to actually fix the inclined plane. And another tools that you're gonna have is the little plank card. This is gonna be your W, and then you're gonna have a set of like masses and 2 hangers. So each of the hangers would have its own mass, so be sure to measure it. And to measure the length, you're gonna have this meter stick that you're gonna be using. So on the first part, first of all, you want to make sure that the inclination is at 30 degree for the inclination. And then from there, as you know that we're going to be doing the measurement of the velocity ratio. So to properly get the velocity ratio, you're going to be wanting to use the meter stick to do a proper measurement of this inclination. Again, be sure to put that knob correctly and then readjust the inclination and make sure it's at 30 degree. And from here, you're going to be using that meter stick as demonstrated in the video. So first of all, make sure that the knob is securely tightened and adjust to the correct angle that you want. And the angle that you want is it's going to be 30 degree as shown in the video. So once you fix it, tighten the knob tightly, and there, make sure it's actually sitting correctly. And from there, you use the meter stick to do the measurement of this inclination. So the video is going to show you in a little bit. So to get the distance s, you want to make sure that you measure the length from the bottom all the way up. So this is going to give you a proper measurement of the distance s, and the vertical height is going to be your y. So be sure to get both s and y, the vertical axis and the inclination axis. So record your s, record your y, and then put S over Y to calculate the velocity ratio. Once you have the velocity ratio calculated, you can start putting this little piece of slab on top of your inclined plane. This piece of slab is going to be your cart that you're going to be pushing upward onto the inclined plane. So whatever weight is being put on here is going to be your W in the equation, and this is the material that we're going to be making work in order to get it across the inclined plane. And from there, what you want to do is you want to stick the little piece of string onto the pulley, and then you want to hang the lighter hanger onto the other side in order to balance the system. And this whatever weight that's being put on the hanger here is going to be your F that is being pushed onto the weight W. So the left hand side right here is going to be your F, and the right hand side or the cart that is sitting on the inclined plane is going to be your W. Right here you're going to be sticking more weight on top of these little hanger here in order to make the cart move. But then again, in order to get the cart moving, you want to get it into the kinetic equilibrium. And by kinetic equilibrium means you want to put more mass onto the system such that it barely moves upward once you give it a little push. So this video is going to show you a little bit. So right here, the demonstrator put more weight up here. So if the weight is too much, then the cart is going to start moving by itself. This is not kinetic equilibrium. This is when the force on the left hand side is way higher than the right hand side. So what you want to do is you want to reduce the weight in order for this to stay in kinetic equilibrium. So according to the instruction, you want to put a 50-gram mass on top of your little slab. Keep in mind that your W is going to be the total mass of the slab plus the 50-gram there, and that's going to be your W that you're going to be using to calculate. Keep in mind that once you increase the W, you're going to want to increase your F, and if you actually achieve the kinetic equilibrium, once you tap the slab upward a little bit, you should see it move with a constant speed, not accelerating. So through this lab, you will be adjusting the weight on both sides in order to experiment with this little machine tool here. Second part is a two-system pulley. So a pulley is when you have this little rolly thingy and you wrap the string around. And with this string wrapped around, you can actually push the force here once, but then again, the force is being pulled by the number of times the string actually wrap around a pulley. So in this case, it would be 1, 2, 3, 4, 5, 6. So there's 6 times the string tension in order to pull this up. Again, you're going to be pulling this distance a lot longer than this thing is being lifted up by the amount of 6 fold. But then again, you could actually get the velocity ratio to be the distance s divided by y, and that is going to be equal to n, and n is the number of the string that is being wrapped up here. So in your setup, you'll be counting the number of string that goes through here, and then do the measurement on the velocity ratio. Again, once you have the velocity ratio, plug it into this equation and you get the friction. And you know that F is going to be the weight that is being hung here to do the work, and the W is going to be the amount of weight that you have on this. Shown here is the actual setup of the two-system pulley. So a two-system pulley is comprised of many strings that are wrapped around, and this little brass hanger here is going to be the weight W that you want to lift, and the number of the string that are being tied and pulled over the pulley is going to determine how much velocity ratio it's gonna give you. So what you want to do is you want to be pushing these strings by hanging the mass onto the hanger on the right, and then the hanger on the left is gonna give you the advantage that is given by the equation that we set here. And the number of rolls of the string that are going through the pulley is gonna give you the velocity ratio as previously mentioned. So first of all, you want to be able to measure the velocity ratio. So you're gonna have the mass hanging on the right and the mass hanging on the left. So once you push the mass on the right down, the mass on the left is gonna go up. But as you can see, that the mass on the right goes down significantly. But then again, the mass on the left, it moves up very slightly. So what you want to measure here is there's going to be a meter stick right next to the machine, and that is going to give you the velocity ratio by measuring how much the mass on the right is moved down and the mass on the left is being moved up. And from there, you could calculate the velocity ratio and the mechanical advantage that you gain from this machine. Keep in mind that the mass on the right is going to be your force F that you're actually exerting on the system, and the mass on the left is going to be your W, the weight at which you're trying to push up. And from there, you could calculate the friction and everything else inside of the system. So again, you want to achieve the kinetic equilibrium by putting the mass in such that once you tap it a little bit, the mass move up. The mass on the left moves up at the constant speed. Part three is going to be wheel and axle. So wheel and axle is basically you have like a much bigger wheel up here, and you have the axle that is like all the way here. So this by using this setup, you could hang a weight up here, and lift it up with a force that is being pulled down here. Again, this wheel and axle system is set up such that you would have the velocity ratio of 2 big R divided by R2 minus R1, where R1 and R2 are the radii of these two axle, and then you would have the wheel of the radius big R up here. So in the lab, you will have these numbers, and you can use it to calculate. And the lab would actually ask you to measure S and Y, where those are the distance where the force and the W is being pushed at a distance. And then from there, once you have calculated the VR, you could actually make an estimate of the friction. Once again, once you know F, W, and VR, you can calculate this guy and then calculate the of the machine. So now that you have the equations ready, so this is the actual setup for the wheel and the axle setup. So the radii is going to be given on the actual setup. I'm sorry, this is in Thai. I'll be sure to point out which number is what number. And now you're gonna see that the mass is being hung to the right. Is the brass right next to the pulley. So this little brass here is gonna be your W. So be sure to set the pulley upright and make sure that the string actually goes under the pulley and hang the mass hanger carefully on the bottom. So this is going to be your W. W is going to be that little weight on the right, and then you're going to be adding the mass on the left as your F, and that's going to be the force that you'll be exerting onto the system. And as you can see, again, obviously, as you move the mass on the left, which is the F, it's going to move like a lot, but then again, the mass on the right, which is W, is going to move very, very little. So first of all, before doing any measurement, be sure to calculate the velocity ratio and then slowly add the mass. And if you add too much of the mass or too little of the mass, it's going to start moving by itself. So again, tap it and try to achieve the kinetic equilibrium in order to proceed with this lab. Again, be sure to record the F and the W just like last time, and use the F and the W and the velocity ratio that you have in order to calculate the friction and the efficiency of the system based on the equation that is given in the lab manual.